Wait, actually, I seem to have not pressed the broadcast button first. So now I am, and people are coming in. So just give it a second for people to come in.
All right. Good afternoon, everyone, and welcome to the 3 p.m. press conference on Tuesday, June 2nd. This conference will be on planets, exoplanets, and brown dwarfs. My name is Susanna Kohler, and I'm the editor of AES Nova. I'll be hosting this conference along with my co-hosts, Rick Feinberg, the AAS press officer, and Tharani Kanchati, the AAS media fellow. They'll be helping out with the Q&A and keeping an eye on any technical issues that come up. For today's conference, we will have 4 press releases, I believe, going out shortly. So look for those. They'll be covering 3 of the presentations today. And all of yesterday's webcast videos are online, as well as all of the presentation files and press releases from yesterday's briefings. They're all in the online press kit on the AAS website. And we should presumably have the ones from today up by sometime tomorrow as well. So just a reminder that we are recording this and we're streaming it to YouTube. The way this is going to work is I'm going to give a brief introduction to the topic and to the panelists. And then the panelists will go through and each of them will give their presentation in order. We won't interrupt them, and then we'll take questions and answers at the end of the session. In terms of Q&A, all of you should have the ability to use the Q&A feature at the bottom of your screen to type your questions, and those will pop up, and you should be able to view the questions that other attendees have put in as well. So you can comment on those, you can upvote them if they're questions that you also have. And then at the end of the presentations, we'll go through and we'll read those questions to the panelists and they can answer. We're opting to do that as opposed to trying to have the speakers answer the questions in real time via text, because that's a little distracting. So the topic for today, as I said, is planets, exoplanets, and brown dwarfs. We gathered all the planetary mass-ish objects into one session. So we'll be starting in our own solar system and moving further out. The speakers in order are Matija from SETI Institute, who will be talking about evidence for a past Martian ring from the orbital inclination of Deimos. Next, we'll have Benedict from University of Texas, Austin, who will be presenting Old Dog, Old Tricks, Old Data, a mass for Proxima Centauri C. Then Benni from Acton Sky Portal will present the first discoveries coming from the Galactic Plane Exoplanet survey. And lastly, we'll have Maria Schutte from the University of Oklahoma presenting the discovery of a young nearby brown dwarf with a disk. So I am going to go ahead and turn it over to Matija to start his presentation, and the rest of us will all turn off our cameras and mute.
Okay, sure. Let's see. Are you seeing a presentation view?
Not yet, no.
Okay, let's just stop it for a moment. This seems to work. Okay, let's see. Okay, let's see now. How about now? Still no luck?
Still not presentation view.
Okay, this will work. Um, yes. Okay, are we in business?
Yes.
Excellent. Thank you so much. Sorry for the delay. So my name is Matija, and I'm going to talk a little bit about what we can say about past ring of Mars from the orbital tilt of its moon, Deimos. And this is the work I did with David Minton at Purdue and the rest of his group. So here you see to scale diagram of orbits of Phobos and Deimos compared to size of Mars. So Phobos is much closer in than Deimos, and also their sizes are kind of to scale. So Phobos is quite a bit bigger than Deimos. What I'm concentrating on is their orbits, which are not exactly in the plane of Martian equator. We think that they formed from a disk around Mars. So they're very close to the plane of the equator, but not quite. Phobos has moved around quite a bit, and we think we understand its inclination, but for Deimos, there has been no explanation so far, and that's something that this paper is about. So this is one of James Keen's sketches from DPS, and this is of Andy Hasselbrock's 2016 DPS talk, where he presents his paper that later became Hasselbrock and Minton in 2017, which is the background for our paper. So what they propose in 2017 is that Phobos is just the latest of a cycle of rings and moons around Mars, where you start with a ring, which then at its outer edge forms a moon, and then just like in the Saturnian system, interaction between the ring and the moon make the ring shrink while the moon moves outward. Eventually, the ring falls into the planet and only the moon is left. However, the moon is interior to synchronous orbit. That is to say, it goes around Mars faster than the Mars spins. And just like Phobos, the moon will always start moving inwards and falling towards Mars once the ring is gone, because the ring is the only thing pushing it out. Eventually, the moon will get very close to Mars and get torn apart by tidal forces, forming a new ring. So Hasselbrock and Minton have proposed that this cycle has happened many times in the history of Mars, and every time you form a new moon and a new ring, they're always smaller by a factor of few. So the um, past ancestors of Phobos were much larger than Phobos itself. So this is a plot from their paper. And what you see here are these dots falling in. Those are the moons, and different colors are used for different generations of the moons. So the purple one is Phobos at the very end, and you can see the cycles become longer as there is less and less mass. In between, you have rings that take a while to form a moon and disappear, and these cycles are also longer and longer. Now, what is really interesting for us is that the outer edge of the ring, technically the fluid Roche limit, is, and that's where much of the action is between a moon and the ring, is where the resonance with Deimos is. That is the place where a moon has 1/3 of the orbital period of Deimos. And these orbital ratios that are integers are also known as orbital resonances, and they're the places where you can have a strong interaction between moons. And most importantly, this distinguishes this theory of cyclic moons and rings from every other theory of the origin of Phobos and Deimos. There is a period of time where the inner moon, which we call proto-Phobos, will be moving outward from the ring because of ring torques. And crossing this resonance with the inner moon moving outwards, meaning that the orbits are coming closer together, is very different from them moving apart, as Phobos and Deimos do now, and crossing the resonance. Only when the moons are approaching each other, you can get capture into resonance and a big effect on the inclination of Deimos. So this is a plot of the final results of our numerical simulations. So what happened here was that the inner moon pushed Deimos around a bit as it was moving out, pushed it through a resonance, and resonance breaks at different inclinations of Deimos, depending on the mass of the inner moon. We change different things, those are different colored dots, but really the only big effect is the mass of the inner moon. And we can say that the present inclination of Deimos, which is about 2 degrees is best matched with the resonance with the prior moon that was about 20 times mass of Phobos. And when you compare that to the model of Hasselbrook and Minton, that's kind of what they call the third cycle. Remember, they count from the present. So this is the grandparent of Phobos. And this should have happened around 3.5 billion years ago, more or less. And other constraints we have on the bombardment and survival of Deimos match that very well. So to summarize, we find that the past inclination of Deimos, the orbital inclination of Deimos could have resulted, as far as we can tell, only from an orbital resonance with the protophobos. Remember, Deimos has a very circular orbit, so to make it inclined but not eccentric, it's a very hard thing to do, and this is the only mechanism we can think of that does that. To have this mechanism work, we need an outward migration of the inner moon. And for something that's interior to synchronous orbit, the only way to move it outward are ring torques, as far as we can tell. That's the only thing we can think of. So that's a conclusion, and we pretty much fully support all the elements of the model of Hasselbrook and Minton from 3 years ago. So I think it's time to look even further into this model and see what it tells us about the history of Mars. And some of those things include Phobos being very young. So the paper is accepted in abject letters, and since last night, the paper is available in archive. Thank you.
Hi, I hope everyone can hear me now. So I'm going to tell you a little story about Proxima Cen-c. Proxima Cen-c is a recent possible planet found around Proxima Centauri, and it's not Proxima Cen-b, which was discovered a few years back. It might be in the habitable zone of Proxima Cen. All right, so this background picture was taken in happier times when you could actually travel to the big island of Hawaii and take a picture of the Southern Cross, and Proxima Cen is approximately right there. All right, so I'm going to do astrometry. And the definition of astrometry is to figure out how the universe works by watching tiny lights move across the sky. We've all done astrometry. If you've ever been at a baseball game and had an errant fly ball come towards you, if you want to catch it and not get hurt by it, you're doing astrometry. You're measuring positions as a function of time. This guy didn't do a very good job of that. So what we're going to do is we're going to measure the position of Proxima Cen over and over and over again. And the data I'm talking about was actually secured a quarter of a century ago with Hubble Space Telescope. So the idea is to measure that position of Proxima Cen relative to some reference stars over and over again, and hopefully something interesting is going on. So it was with Hubble Space Telescope, and Hubble lets us measure angles with millisecond of arc precision. And what that means is if you hold a quarter up and you're 1,500 miles away from that quarter, that's the angle subtended by the quarter. So it's really quite a spectacular device for measuring positions of stars. So in the old days, a quarter of a century ago almost now, when we published this, we actually looked for planets around Proxima Cen by doing astrometry. And this was before anybody knew exosolar planets existed. Exoplanets were there. So we were trying to do discovery. So we made these measurements, but we found nothing. We found nothing, but we only looked for companions with periods shorter than 1,000 days because we had about 2,000 days of data. In February of this year, this was announced. So Damaso and his crew decided that there might be something else orbiting Proxima Cen. And this something else, the evidence for this was in the radial velocity method, where you see that Proxima Cen is coming towards you and going away from you in a rhythmic fashion. And it turns out the period they found from that data, from the plot in the bottom, where if you're a skeptic, you might actually say, there's maybe not anything there. But for me, to test this, we actually had the data that we could test it. So the question is it a real planet or not? So we've done a whole lot of work on this sort of thing. Astrometry of exoplanet host stars combined with radial velocities, and we've come up with a bunch of masses for these things and could tell people that, yes, you actually did discover a planet, not a binary star. And so it's almost like a doctor hitting your knee. Your leg's going to jerk. Well, I saw, hey, there's radial velocities available now. Let's do something. So the something we did was back in March and April of this year. So it's truly an old dog, me doing old tricks, which is FGS astrometry and radial velocity with old data. So this quarter of a century old data. And we published the results in the research notes of the AAS. And it looks a little ratty. Those are the residuals, but there is an orbit there. So what we found from this, we could estimate the mass of this new planet as about 18 plus or minus 5 Earth masses. So it's about the mass of Uranus. So from combination of radial velocities and astrometry, yeah, that's a real planet. It actually does exist. And coincidentally, Cervella and his crew deduced from Hipparcos astrometry and Gaia astrometry and the proper motion changes between Hipparcos, which was 20 years ago, and Gaia, which is ongoing right now, that there was something there with about that mass. So we agreed with that. So this is not the end of the story. This is a fast-moving target here. Later in April, this came out. So searching for near-infrared counterpart of Proxima C using this high contrast imaging system called SPHERE. And with great effort, these guys teased out 9 separations in position angles covering 3.3 years of a 5.5-year orbit. This is one of their best pictures. And so that's the planet there. And so the question is, really, is that the planet? Because there's a whole lot of little specks on that picture that you could say were planets. So with their data, I can fit an orbit. And it looks pretty good, actually, considering that 2/3 of their paper was trying to explain away this as being an artifact of their machinery. The orbit that they came up with was really very good indeed. So what we're doing with Hubble is measuring the position of Proxima, which in this diagram is the blue thing in the middle, measure that as a function of time. And Grattan and these people have measured the red thing that's going around them. So 2 orbits that we can work with. And it's just like doing a binary star, which is something that I and my team have done over and over again. So we've combined modeling. We've got prior information from the radial velocity orbit. We have our astrometry of Proxima Cen A, which is the host star. We have the SPHERE astrometry of the planet itself. And we get a perturbation orbit and an exoplanet orbit. And then we get what's called a mass fraction, which means we now have masses for both components. And so the end result is for Proxima Cen A, which is the host star for the planet, we get a mass of 0.097 plus or minus 0.007 solar masses. But we also get the mass for Proxima Cen C. And now the mass is shrunk. It's now 7 plus or minus 2 Earth masses. And the reason for that is that the orbit from the SPHERE data is so good that it's forcing the inclination of the system to be a higher inclination, which means the mass of the companion has to be lower. But we have a little bit of a check. We've got a mass luminosity relationship for stars. And does Proxima Cen agree with that? And it turns out that it does fairly well. So here are our conclusions. The astrometry plus radial velocity yields something the size of Uranus, or the mass of Uranus. If we add in the SPHERE results, we get the mass of C being really a super Earth. And so there's a tension between these 2 mass estimates. And so does that indicate a possible issue with the SPHERE measurements? Which if there's a question about that, I could talk later. But seriously, you need more SPHERE observations of Proxima Cen C. And there's a huge frustration with that because, ESO, the European Southern Observatory, is closed because of COVID-19, and they can't make these additional measurements this year. So we have to wait till next year. On the other hand, Gaia is going to significantly improve the Proxima Centauri perturbation, but we won't get those results until 2025. So anyway, this is like a little wave and a tidal wave of information about this. And I don't know if I'll ever do anything else on this, but it was sure a lot of fun to do it now. So thank you.
While Paul is getting set up, I just wanted to take a minute. I forgot to mention, when you submit questions to the Q&A section, please mention your affiliation and your name and who you are asking the question of, as has been excellently modeled already with our first question. Thank you.
Okay, I'm Paul Benni. I'm an amateur astronomer. I don't have any affiliations. And my presentation's on the first discoveries of the Galactic Plane Exoplanet Survey. The goal of the GPX survey is to look at high density star fields of the Milky Way to see if there are transit-like events that could represent exoplanets. This survey is complementary to ground surveys that has been done in the past, and also tests, is because they tend to avoid the high density star fields because the stars tend to blend together in the images. So GPX is a higher resolution study than the ground surveys and tests. Okay, this is Acton Sky Portal. It's as it looks, a residential private observatory in my front yard in front of my house. On the left side is a RASA 11 telescope. It's a wide field telescope, and this is the telescope that we use for the survey. On the right-hand side is a C14 telescope, and this one is used to follow up on exoplanet candidates. Besides GPX, I participated in TESS, KEL, EXO, MASTER, and it's really, to learn how to do this, you got to know how to follow up on candidates and get good results. The reminder, the transit detection method is used to find exoplanets as shown by the figure. Artem Burdanov, who's the second author, started the KPS prototype survey when he was a master's student, and I joined him, and what we did is we experimented with survey telescope configurations. We went from the very simple, and from what we learned, we expanded our ability. And Artem also developed the data processing pipeline for the surveys to process the data and generate phase plots and light curves for us to look at. The first discovery, KPS-1b, is a transiting hot Jupiter. The host star and the planet are similar to the sun in mass and radius, but with an orbital period of 1.7 days. So it's like our Jupiter being very close to our sun. The validation for KPS-1b to be an exoplanet was done by SOFI using radio velocity techniques. I consider this very lucky to find this, because if you look at the field here, the white box represents the field that we surveyed. We looked at this field over a few months with my telescope and just imaged it, just like stared at part of the sky. And so the funny thing is, if you look at the Big Dipper there, you see the pointer stars. So now you can say that, okay, the pointer stars also point to an exoplanet. And another funny thing about this is that when I tried to describe this to my young son, he called it the lucky duck planet. This is our publication. And from this, it inspired us to upgrade the camera and add multiple field surveying capability to the Rosetta telescope. And this became the GPX survey. Our discovery in a GPX survey after a lot of false positives is GPX-1b. It's a transiting brown dwarf. It's a low mass brown dwarf, about 20 mass Jupiters. The atmosphere is possibly inflated due to the radius being a little bit larger than typical brown dwarfs. The star for this system is larger than our sun and hotter, and it has a period of 1.74 days. Also, this system, we determined it to be fairly young, and this might lead to more investigation as how young this system really is. What's interesting about this is GPX-1b was discovered before the test satellite was launched, and we wanted to see what this would look like with tests. So on the left-hand image is what the Rosetta telescope would see at a resolution of 2 arcseconds per pixel, while the test image at 20 arcseconds per pixel is on the right. The yellow arrow points to GPX-1. So as you can see in the test image, it'd be kind of hard to figure out exactly where the star is unless you knew exactly where to look. And because of the 9 magnitude star, the transit signal was heavily diluted. And you really had to know exactly what pixel to look at on the test image to define the transits. Another interesting discovery is a pre-cataclysmic binary. What's interested in this is a K star and a white dwarf orbiting each other. And the white dwarf is eclipsed by the K star, and it forms 10-minute eclipses, as shown by the arrow. The 10-minute eclipses are very sharp and box-like in shape. So this, to us, was determined that the object is a very compact object. And radial velocity measurements indicated the mass, which is a white dwarf. And another thing interesting about the light curve is the red wavelength transits are deeper than the others. And usually for white dwarf type eclipses, it's deeper in the blue. And so we believe that this suggests accretion activity. The period of this system is 7.1 hours, and calculations that we've done in our paper, the system might start to nova in about 9 million years. Another interesting thing about this system is that the light curves, the variability is changing. The transit depths are changing. So when we looked at it several months later, the transit depths were less, and the shape of the light curve changed as well. This is published very recently. GPX started with Artem and I. We grew over time with observers around the world. Professional astronomers helped us as well to get observations on larger telescopes and SOFI. And these are some of the contributors that came on to help us with GPX-1b. And that's my presentation. Thank you.
Hi, everyone. I'm Maria Schutte from the University of Oklahoma, and I'll be presenting today on the discovery of a nearby young brown dwarf with a disk, which you can see here in this artist rendition done by citizen scientist William Pindrell. So the first major question to think about is, how do brown dwarfs form? Brown dwarfs are objects with masses between that of stars and giant planets, with this mass range being from around 13 to 80 times that of Jupiter, which means they don't have enough mass to fuse hydrogen in their core like higher mass stars. The big question of, do these objects form more like stars where they collapse from a molecular cloud, into a rotating circumstellar disk surrounding the proto-brown dwarf, or do they form possibly within the circumstellar disks of larger mass systems, more like a planet, and then they get ejected from that system by some mechanism, is still an active area of research. And we found that one of the best ways to study this brown dwarf formation is to look at these objects when they still have young disks surrounding them. These circumstellar disks are disks of gas and dust surrounding stars or brown dwarfs in this case. And you can see here on the right a famous image from ALMA of HL Tau. And these circumstellar disks are important because it's expected that that's where planets form. So we made this discovery using the Disk Detective Citizen Science Project, which was designed to find new disk systems by using the power of thousands of people around the world to mine through NASA WISE mission images. In its first iteration, they classified over 412,000 objects, and previous WISE disk surveys had false positive rates of over 90%. And we found that one of the best ways to combat this is by visually inspecting images, like you see here on the right, which is what citizen scientists and scientists see as you flip through multiple wavelengths of light, and then you can choose one of these options for each object. And this would be impossible to do for one person for this many objects. One of such objects that we found was this WISE long telephone number, which we call W1200-7845. So we then confirmed that W1200-7845 has a disk by plotting its brightness versus wavelength. And as you can see in this tan shaded region, this is what you would expect from this plot if this object had no disk. But what we actually see in our gray points here is that there is an excess at these longer infrared wavelengths, which points to the presence of warm dust and gas surrounding this object. Also from this plot, we could estimate the most likely mass for W1200-7845 is 42 Jupiter masses and has an effective temperature of about 2800 Kelvin, which puts it firmly in the brown dwarf regime. We then confirmed that W1200-7845 is in a young moving group. A moving group is just a group of objects that move together in the sky and are expected to have formed around the same time. And we confirmed this by plotting the space motions of everything nearby in the southern sky. And we saw that W1200-7845 is in this green group here, which is the Epsilon Chameleontis moving group, or Epsilon Cha. And this group has a bulk age of about 3.7 million years old, which is very young. We further confirmed that W1200-7845's spectrum is consistent with a young brown dwarf by attaining a near-infrared spectrum from the 6.5 meter Magellan telescope in Chile. And then we compared it to other young brown dwarf spectra. As you see here on the right, our object is in black and the other spectra are in colors. So to reiterate, W1200-7845 is a nearby young brown dwarf disk at a distance of about 102 parsecs or 332 light years. This puts W1200-7845 in our local neighborhood. As you can see here on this plot on the right, we've plotted distance versus age for brown dwarfs with disks that have readily available masses and are in known moving groups. And as you can see, there is a lack of young objects in our sort of local neighborhood, which extends out to around 100 parsecs. And just to reiterate, brown dwarfs are known to have disks, and there are objects brown dwarfs with disks that are younger and farther away. And there are also objects that are older but closer to us. So what makes our system a little bit more unique is that it is less than 5 million years old and relatively close to us. So in conclusion, W1200 7845 is a young, about 3.7 million year old nearby brown dwarf disk. And this can serve as a benchmark brown dwarf disk for future brown dwarf formation studies due to its youth and its proximity. And its proximity is especially important because it's at an ideal spot to get high resolution imagery, sort of like we saw with the HL tau image I showed at the beginning. We could also learn more information from follow-up observations such as the disk's mass and radius, and if it's still accreting. Additionally, please help us find more nearby young brown dwarf disks, possibly in Disk Detective 2.0, which has 143,000 more objects to classify and launched yesterday, June 1st, 2020. You can learn more at our website, diskdetective.org, and on Twitter at diskdetective. Finally, I want to finish by acknowledging that the funding for this research was provided by NASA's Exoplanet research program, and I want to thank all of my fellow researchers who helped with the paper, which has been submitted to AAS journals. I'd especially like to thank the Disk Detective PI, Mark Kuchner, and especially the citizen scientists, Milton Bosch, Hugo Durantini-Luca, Jonathan Holden, and Michihara Hyogo, who were the first people to classify and identify this object with Disk Detective. And there is my contact info again. Thank you.
Great, thank you so much, Maria, and all of our speakers. If you would all like to go ahead and start your videos, we will move into the Q&A section. So it looks like we've got at this point 3 questions in. So Tharni, you want to start out?
Sounds good, yeah. The first question is for Matija. It comes from Stephen Lawrence of Hofstra University. Are there predictions of the size distribution of the ring particles? If there had been several generations of ring debris accreted onto Mars, would any chunks be large enough to survive an impact on the planet? And would this scenario predict an enhanced density of craters, perhaps small, in the ring plane on Mars?
Yeah, it's a very good question, and one that is a little bit beyond this paper, and we need to look into this in more detail. In the original Hasselbrock and Minton paper, they're looking at foot across particles. So when they go into the atmosphere, I don't think they would make a crater. They might disintegrate. So definitely there might be piling up of material at the equator, but actual individual craters are unlikely, probably.
Thank you. And since these 2 questions came in at the same time, but there's another one for you. This is from R.A. Lovett, no affiliation given. A very similar question to the above one. What does this tell us about the geology and evolution of Mars? What would the surface have been like when the ring was collapsing? Would this have been a problem for life, or are the particles too small and scattered for a killer bombardment, assuming there was life, of course?
Yeah, so it's a little bit outside of my specialty, but these rings will be falling in over long periods of time, and it'll be kind of like a rain of dust. So I don't think it'll be particularly cataclysmic. Obviously, dust in the atmosphere can have environmental effects, but I'll leave that to my colleagues to look into that and think more about that.
Thank you. Okay, this question is for Paul. It comes from Francisco Mendez of the University of Florida. 2 questions, really. So first question is, what software did you use to write the pipeline for KPS? And the second question is, what are the limitations to your instrument in terms of V magnitude and transit periods?
Okay. First question, Artem developed the pipeline using public domain components like IRAF, VAR tools, and others. And you can look at my poster for more details of the specific software used, and later Artem will be available for chat to discuss that if you want more. In terms of stellar magnitudes, we looked at from 11 to 14 to 15 magnitude stars. For example, GPX-1b is a 12 magnitude star. KPS-1b is 13 magnitude, and the white dwarf system was 14.7.
All right, thank you. Another question is coming in for Paul. Okay, yes, there we go. It's been completed. From Andrew Fracknoy, no affiliation given. How did you first get interested in this work?
It's an interesting history. I mean, I started as an astro imager, and I mean, I live like, let's say a 40-minute drive outside of Boston, and these are fairly light polluted sky, and I was always disappointed by my images. They never look like the ones in the magazine. So I read the book by Bruce Gary, and I became interested in, okay, can I detect transits from exoplanets? So I gave it a try. After a few attempts, I was actually able to capture one. I think it was WASP 3B was my first one. And from there, it just took off. And there's a Czech exoplanet society that allowed amateurs to post transits. I posted like about 150 on there. So I got experience doing it. And then there was the professional surveys. They asked for follow-up people. So I volunteered and started following up to find new exoplanets. And so I must have observed more than 200 exoplanets, collected data and so forth. And that's how I became experienced with this.
Thank you. So this question is from Matija from RA Lovett. How much material was in each generation of rings, and how big was the proto-Phobos, the most recent one and the earlier ones? And how many generations of moons does the model predict, and how big was the biggest?
Okay, so from the Hasselberg and Minton paper, they had 6 or 7 generations of moons, but that number is actually not very well defined because the cycle is very short early on. So that is to be determined by the modeling of the formation of the original disk, I guess, from the impact or something else. Now, this is the third Phobos ago, and it had about 18 to 20 Phobos masses. So the one in between was about 5 Phobos masses. And in each cycle, about 20% of the mass goes into the moon and the rest falls into the planet. So the ring we're talking about 3.5 billion years ago was maybe 100 Phobos masses to start with, but then might have decayed quite a bit by the time this resonance happened.
Great, thank you. Question for Paul from Noreen Grice. You can do astronomy. Do you involve local students in your observing, and by students, high school / college students, as part of the observing program?
Not really, but I do volunteer when schools have like star parties, and I bring a smaller telescope to the star parties, and I know exactly how to entertain the students, you know, like what targets are the most entertaining to them, or all, you know, all wise. And so I do that. And yeah, that's how I see.
Thank you. Another question for you, Paul, from Karen Collins of the Center for Astrophysics. As a citizen scientist, what is the most challenging part of bringing a discovery to publication?
Okay, that it is very challenging. I did write a first draft of GPX-1b paper, but as Artem went through all the data and stuff, my draft kind of disappeared. It's not easy. It's probably the most challenging part in finding an exoplanet is trying to publish it.
All right, thank you. This question is for George from Steve Lawrence of Hofstra University. Would ALMA be able to resolve and detect the thermal emission from Proxima C?
It's a good question. Hi, Steve. The issue of the optical detection is how can you have something that's 10 times the mass of the Earth be bright enough to be seen? And one of the explanations is, does it have Is it a planet with a giant ring system, or is it just a great big blob of dust? If it turns out it's a big blob of dust, then yeah, ALMA ought to be able to see it. But if it really is just a planet, it's not clear to me that there would be enough millimeter radiation reflected from that for ALMA to see it.
I just wanted to step in real quick to note that Matija had to leave for his oral session. So apologies that we didn't get to all the questions intended for him.
Yeah, and I think that question for George might have been the last one, unless the panelists would like to ask each other questions. Or Rick or Susanna or myself, though I don't have any questions right now. Oh, question just came in for George from Christine Pillion, SETI, I believe. Is there additional Hubble FGS data from 2000 or later that could be analyzed? If so, would it help refine the numbers further?
Hi, Christine. Yes, if there were more data, that would help refine the numbers, but we stopped observing Proxima in 1997, and as you probably well know, a proposal to do astrometry with defined guidance sensors on Hubble Space Telescope right now is almost instantly rejected because Gaia can do it better. And so where we're going to get the new data to do the refinement is through Gaia. So Gaia is looking at this thing probably 150 times over 5 years, and we'll have a really an excellent perturbation orbit, not just for the outermost one, but for the inner one as well, because the signature there is something like 10 micro arc seconds. But if Gaia performs as hoped, we'll actually have a perturbation orbit that's got 2 components to it. And that's going to be pretty spectacular. But then, as I mentioned, you'll have to be patient because we won't get those Gaia results for another 4 or 5 years.
Thank you. And I believe Rick has a question for Maria.
I do. Thank you very much. So I keep seeing reports now of tremendous advances in machine learning, and I've seen even some comments in press releases about this, saying that whereas in the past, computers couldn't do the kind of thing that you see in disk detectives or Galaxy Zoo, for example, that it's getting to the point where machine learning and AI is getting able to do that. So I'm wondering if you have any sense of the future of citizen science projects like yours that require or that benefit from lots and lots of humans looking with their eyes and brains and doing this kind of classification and making fine judgments. Do you think, I mean, we've been in a golden era of that, but do you think that we're getting past the peak or approaching a peak, and or do you foresee that these kinds of projects may not have an infinite lifetime?
Right, that's a good question. So I know previous similar disk surveys that have done work with machine learning still have pretty high false positive rates. They're lower than older ones. So I think until that number gets down to what we're seeing with the way citizen scientists do it, which is in like 7%, I think. I think until the machine learning algorithms can get down to that low of a false positive rate, there will still be a need for citizen scientists to actually mine through all of these images. I think even too with machine learning algorithms, where they might reach that false positive rate eventually, there'll still be a need for, there'll still be lots of these systems that will need to analyze and will need to double check to make sure they're not false positives, and that will really benefit from still humans looking at all of the images.
Great, thank you.
I actually want to ask a follow-up question, which is, what kind of involvement have you been getting with Disk Detective? How many people are turning up and classifying things? How long does it take to get through a data set?
Right, so Disk Detective 1.0, when we classified over 412,000 objects, started in 2014, and we finished in last year, in 2019. So that's about how long it takes, but we have less objects for Disk Detective 2.0, so it won't take quite as long. So that's the involvement there. And with our beta testing, we finished all of our objects for beta testing for Disk Detector 2.0 in about a week. So
Do you know how many people were involved in that?
I'm not sure the exact number, no, but a pretty good amount. I would say at least 1,000.
So behind every successful scientist are 1,000 citizen scientists.
At least.
All right, I don't see any more open questions, so last call. I guess I'll hand it back to you, Susanna.
Okay. Well, I want to thank all of our speakers again so much for being here, and thank you to the PIOs who helped with the press releases and the briefing preparations. And thanks to everyone in our audience for being here. The next press conference is going to be tomorrow morning at 11:15 Eastern Time. The topic will be the mysteries of the Milky Way, and I will be hosting that one as well. So we look forward to seeing all of you there. Goodbye.
Thank you.
Hey, everyone.
Thanks, guys.